Good day, everyone. This is going to be the video lecture for Chapter 2 for the Physics 1000 summer session. In Chapter 1, we talked about scientific method and basic motion of objects. And now we're going to talk a little bit about why things move, how we make things move. We're going to cover a lot of different topics, like a lot of different subjects, categories within this one presentation. So I'm going to step you through the slideshow, sort of tell you where each subtopic is beginning and ending, so that you can go back and rewatch just any specific parts you need to as you need to. So let's get started. If you pull up the slideshow for Chapter 2, Newton's Laws and Basic Mechanics. If you move on from the title slide to Slide 2, we're beginning with an excerpt from Sir Isaac Newton. Isaac Newton is one of the most famous physicists of all time, and he is especially famous for giving us Newton's laws of motion. Famously, he did so utilizing a lot of his research, famously, colloquially, stemmed from watching an apple fall. And, well, there's a bit more to it than that. The motion of the apple can be explained using Newton's 3 laws of motion, which we are about to discuss. If you move on to Slide 3, Newton's laws are they are actually incredibly important to studying the physical universe around us. And this is real physics. These are real physics laws that meaningfully affect everything we do in our day-to-day lives. So this is very important information. An important note to make, Newton's laws deal with both mass and with force. Now, those two things are different. They are different things. Mass represents the amount of matter within an object. So this apple contains a certain number of atoms and molecules, and mass represents the physical amount of stuff contained within this particular apple. Mass is measured in grams, it's also measured in kilograms, and it's just a measure of matter. Force, meanwhile, is a measure of the amount that you are pushing or pulling on something. Now, this apple by itself will always have mass, but the outside world has to exert forces upon the apple to get it to do anything. This apple has a certain mass. It will sit in my hand forever until some force outside of itself does something to it. So, its mass is constant, but the forces around it are going to change. Mass and force are different things. Important thing to note. Now, on to Newton's 3 laws of motion themselves. Just to go through them in order, the first law of motion states, an object at rest will remain at rest, or an object in constant motion will remain in constant motion unless acted upon by an outside force. So, if I have this apple in my hand and I leave it here, if I never touch it again, it is currently at rest, and if nothing ever affects it, it will remain at rest. Currently, it is not displacing, it is not moving, it is not accelerating. All of those attributes are remaining 0 until some outside factor exerts a force on the apple to change them. The apple is going to remain in my hand until something outside of the apple changes. I can take my hand from outside the apple and exert a force upwards that will cause the apple to begin accelerating upwards. But if I don't do that, it will stay here. That's half of Newton's first law of motion. The second half states that the same thing happens if an object is moving at constant velocity. So if the best example of this actually is outer space. If you've watched much sci-fi, or even watched much in terms of actual videos of things happening in space, like on the International Space Station, or representations of meteors, planets moving through space. An interesting thing about space is there's no air to slow you down, and most of the time you are not near a planet to affect you meaningfully with gravity. So things tend to float through the vacuum of space forever. If I was in space and I threw this apple, and say I threw it at 5 meters per second, it would just keep flying at 5 meters per second forever. If an object is at constant velocity, it's going to stay at constant velocity until something outside of it slows it down. So in space, if I threw this thing, this apple, it would keep moving forever in the direction I throw it until it hits something or something else happens to it to slow it down. We don't observe this on Earth too often because on Earth we have things like friction constantly slowing us down. If I was to throw this apple here on Earth, air resistance, air friction would slow it down as it flies, and then gravity is going to pull it towards the Earth. But if you can completely eliminate all outside forces, Newton's first law says, an object that is in constant motion, moving at a constant velocity, will stay that way until acted upon by an outside force. All objects like to stay how they are. It takes effort to change it. So whatever state the object is in, it wants to stay there, and you have to exert a force on the object to change it. If it's stationary, you have to exert a force to make it move. If it's moving, you have to exert a force to make it stop. And that's Newton's first law of motion. Newton's second law of motion is actually a formula. And I'm going to write that formula up on the board behind me just so that I can point at all the parts of it. So, this symbol right here is the Greek letter sigma. This, in physics, we use this symbol right here to represent sum of. And I'm going to write that out because the spelling is important. S-U-M of. This is not S-O-M-E of. This is S-U-M. The mathematical sum of F. Whenever you see this symbol in math equations, it means mathematical additive sum of whatever it is applied to. So, right now, this symbol is being attached to the letter F. And in all of our formulas, a capital F is going to represent force. So, Newton's second law is a formula that begins with the sum of all of the forces acting on an object is going to equal the object's mass times the object's resulting acceleration. So, when I hold this apple in my hand, there's multiple forces already acting on this apple right now. Gravity from the Earth is pulling it down, and there's a force from my hand pushing it up. I have to exert a vertical force on this apple right now. So, currently this apple's acceleration is 0. It's not accelerating anywhere. It's remaining at constant velocity. And that constant velocity is 0. It is at rest. Since its acceleration is 0, if this term is 0, that means this whole side of the equation would equal 0, because mass times 0 would be 0. And that means that all of the forces, some of the forces, had to add up to 0. So when I am holding the apple like this, and it's not accelerating, because all the force, because we can tell it is not accelerating, it is just remaining at rest. That means all of the forces currently acting on this object had to add up to 0. That means, say Earth is pulling it down with a gravitational force of 3 newtons. My hand is lifting it up with a force of 3 newtons. They have to be equal and opposite to one another. Gravity is pulling down, my hand is pushing up, so that they add up to 0. And when the forces add up to 0, the resulting acceleration of the object will be 0. So when an object is completely stationary, or when it is moving at constant velocity, in both of those cases, the acceleration is 0, therefore the net force, the sum of all of the forces on that object, have to add up to 0. If you want to keep moving at constant velocity, whether or not that constant velocity is something other than 0 or is 0, all of the forces on the object have to be balanced. Any stationary object, like my chair here, if it's not accelerating, all of the forces on it have to be balanced. Gravity's pulling it down, the floor is pushing up. Those have to be adding up to 0, because if they add up to 0, 0 equals mass times acceleration. The chair's mass is not 0, but its acceleration is. And that means your two sides will equal each other. 0 equals 0. In order to make an object accelerate, you have to exert an imbalanced force on it. So, if we use the apple for this, let's say, rather than letting the apple stay here, I start lifting my hands upwards. So, the force of gravity on the apple hasn't changed. It still weighs the same amount. Gravity's still pulling down with the same force. But in order to lift it, I am exerting a larger force than I was with my hand. So, to lift it upwards, I am now lifting with more force than I was previously. That means my force upwards is bigger than the gravitational force downwards. So say I'm lifting with 4 newtons of force, where gravity is only pulling down with 3. That means that the sum of the forces, the net force on this apple, would be 1 newton. And that's because, I'm going to draw a diagram here representing the apple. So that's our apple. Previously, when I was allowing the apple to sit at rest in my hand, let's say gravity was pulling down with 3 newtons, and I was pushing up with 3 newtons. Now notice they are pointing in opposite directions. That means they're working against one another. So, when you add them up, you're adding 3 to negative 3, they add up to 0. This is previously when it was just resting in my hand. But, if I was to lift with more force, say 4 newtons, now 4 plus negative 3 is 1 newton. There's now a net force of 1 newton upwards. And that net force is going to cause the apple to accelerate upwards. Your acceleration will always be in the direction of your net force. Net force is the sum of all the forces. So I'm using that term to describe this whole thing right here. Net force. So sum of the forces, net force, mean the same thing when I say them like this. So Newton's second law tells us that the net force on the object will determine its final net acceleration. If the forces on the object are balanced, say these two were the same number but in opposite directions, they'd add up to 0, there'd be no net acceleration. In order to make an object accelerate, you have to imbalance the forces on it. For example, if I allow this marker to just drop to the floor, once I let go of it, I'm no longer holding up. Instead, the only force is gravity downwards, which means that the net force is going to point down, so the marker accelerates down. That is Newton's second law of motion. Newton's third law of motion states that for every action force, there is an equal and opposite reaction force. This one gets quoted and misquoted a lot in just normal everyday life. To give an example, say I lean up against my whiteboard. I'm leaning into my board right now. When I do this, I'm exerting a force on the board. My body is pushing into the board when I lean against it. So the action force is I am pushing into the wall. The reaction force is that the wall is going to push back on me. The wall is going to push back out on me. So I'm pushing into the wall, but the wall has a very large mass, meaning that if this mass is very, very big and I'm exerting a constant force, the resulting acceleration of the wall is going to be very, very small. So when I push against this wall, not much is going to happen. I'm not going to be able to make this wall accelerate because its mass is too big. Meanwhile, when I push into the wall is going to push on me. Now, I'm leaning into the wall right now. My center of balance has shifted so that I'm putting my weight into the wall. The wall is exerting a force on me. If the wall wasn't doing that, if I was holding this same posture and the wall was not there to support me, I would fall. When I am doing this, the force from the wall against me is what's holding me up. So that's the proof that there is a force from the wall against my body. Whenever you exert a force on anything, it will exert a force back on you. When I'm holding this apple, I'm lifting the apple up, therefore the apple is exerting a force into my hand. That's how you can feel its weight. It's pushing into you, literally. Anytime one object exerts a force on a second object, that second object will exert an equal but opposite force back on the first one. Another example is if I sit in a chair. So, when I sit in this chair, I am exerting a force into the chair equal to my weight. I am pushing down into it equal to my weight. The chair is likewise pushing up on me with an equal and opposite force. And the chair pushing up on me is the reason I'm not falling right now. Gravity pulls down on me, the chair pushes up on me, those two forces add up to 0 and I can remain in the chair. Now, sometimes the chair is too physically weak, say it's old or broken, sometimes it's too weak to be able to withstand the force you're applying to it, in which case it would break. So if the object cannot exert the equal and opposite force, if it's not strong enough, it'll just break on impact when you apply the force to it. So those are Newton's 3 laws. They are very important to all of physics, and we're going to refer back to them constantly. So I recommend reading this slide, writing these down for yourself in your notes, because writing things yourself in your own hand will help you remember them. If we move on to slide number 4, we are going to utilize some of these laws in just a very quick math question. So I'm going to draw this in on the other side of the board. I'm going to leave the formula here because we're going to use it. I'm going to draw on the other side of the board a representation of the question on slide 4. So, in this question we have a 500-gram box. The mass of this box is 500 grams. Now, there are 4 separate forces acting on this box in this question. So, let's envision, say this is a very strange game of tug-of-war, and we're looking down on this box from above, and our 4 players are all trying to pull the box in their own direction. So, our first force is 100 newtons upwards. Our next force is 250 newtons to the left. Our next force is 125 newtons down. And our final force is 200 newtons to the... This final force is 200 newtons to the left. This is 250 newtons to the right. So, these are the 4 forces acting on this box. So, what I would like us to find is, to start with, just reading the question, what we want for part A is the total force on this box. We want to find the net force on this box. So we have to add up these forces. Now, as we discussed last time, the x and y axes exist completely separately from one another. If I pull my chair sideways, that's never going to make it go upwards. No amount of sideways force by itself can ever make my chair go up. Similarly, if I lift my chair upwards, that by itself is never going to make it go sideways. So, in order to find the net force on this object, we need to look at the 2 different axes separately. So, we're going to look at our x forces. Our first x force has us being pulled 250 newtons to the right. The other x force is pulling 200 newtons to the left. Now these are in opposite directions. They're working against one another. So, most of the time we're going to assume that the rightmost direction is the positive direction and that the left will be the negative direction. So that means this 200 is going to be pointing in the opposite direction. If this is positive, then this must be negative. And so when we add them up, they're going to add up to 50 newtons. They're not going to add up to 450 because they're working against one another. So, this is going to be our force in the x-axis. Next, in the y-axis, our first force is 100 newtons up, and that's working against 125 newtons down. We're normally going to assume down to be the negative direction, and they're still working against each other, so that's going to leave us with a net force in the vertical axis of 25 newtons. Oop, I forgot my unit labels. I'm sorry. So 25 newtons, that's our number and our unit. And then for our direction, we're going to indicate this is in the y-axis. So, this is the net force in the x-axis, and since that is the net force in the x-axis, that means this box is going to start accelerating in this direction. Then in the y-axis, the net force is negative 25. So in addition to the box accelerating this way, it's also going to accelerate this way. So currently, these 2 players in the tug-of-war game are winning. Keep that in mind. So, part A asks us for the net force on the object. And these right here are the net forces in both our x and our y axis. Great job. Next, we're going to find the total acceleration of the box. So, we have Newton's second law right here. This is a formula that equates force to acceleration based on the mass of the object. So, we're going to use that formula to find the acceleration of this object in the 2 separate axes. So, in the x-axis, force equals mass times acceleration. The net force on the box is 50 newtons. The mass of the box is 500 grams. Now, an important thing to be aware of. Whenever any of the formulas in this class have mass in it, you need to use kilograms instead of grams. Now, kilo is a metric prefix, and in general, 1 kilogram, 1 kilo anything, is equal to 1,000 of the original object. So, all of our formulas for this class, we want to use grams for mass, but we specifically want to use kilograms. So, if 1 kilogram equals 1,000 grams, 500 grams is going to equal half a kilogram. I'm going to do that sample calculation real quick for you guys, just to catch you up to speed. We've got 500 grams. We want to convert that to kilograms. There's 1,000 grams in 1 kilogram. So I'm arranging my conversion like this to cancel out grams and leave me with kilograms. So 500 times 1 divided by 1,000 tells us that the mass of this box is 0.5 kilograms. 0.5 kilograms. And that's what I'm going to plug in here for mass. So our force in the x-axis is positive 50. Our mass is 0.5 kilograms. Now we can solve for acceleration. We're going to divide both sides by 0.5. And so your final answer should be 10 meters per second squared. Remember that meters per second squared is the unit for acceleration we're going to use. So this box is going to begin accelerating at 10 meters per second squared in this direction. Let's check the y-axis. In the y-axis, we're going to use the same formula, but we want to use only the vertical variables. So our y net force is negative 25. So we're going to plug negative 25 in for force. The box's mass is still 0.5 kilograms because mass does not depend on what direction you're moving in. Mass is a scalar, not a vector. So we have negative 25 equals 0.5 times a. That means our final acceleration is going to be negative 5 meters per second squared. Negative 5 meters per second squared. That means the box is going to accelerate down in the negative y direction at negative 5 meters per second squared. So this box is going to accelerate to the left and down at the same time. Realistically, that means it's going to sort of move in this direction. It's going to sort of move southeast. Southeast? Yes, southeast. It's going to move in both of those directions at the same time, and it's going to slide in this direction. So, this is an application of Newton's laws as we have discussed them so far. Before we move on to our next concept in these notes, if you move on to slide number 5, I want to talk a little bit about a very specific force, and that specific force is going to be gravity. So, gravity is a force. It's acting on us all the time because we live on a planet. Planet Earth has gravity. Gravity is a force. It's always pulling down on us. Now, the exact force of gravity is going to depend on the mass of the object. Objects that have more mass, objects that have more stuff in them, are going to naturally weigh more. So if I compare this apple to my metal water bottle that is filled with water, the water bottle has more stuff in it. It's filled with a lot more atoms. Metal is very dense, and this thing is currently filled entirely with water. This water bottle weighs more than this apple. There's more mass in this apple for gravity to pull down on, so there is more gravitational force acting on the water bottle at any given moment. And that's because they have different masses. The way that you find the force of gravity acting upon an object is with the same formula. I'm just going to change two things. I'm only going to change two things to tell you how to find the gravitational force, the weight of an object. So instead of adding up every single force on the object, we're only trying to find one force. So our one force we're trying to find is the force of gravity. So this is F subscript G, force of gravity. Whenever I write Fg, that's what I mean. And the force of gravity acting on an object is going to be equal to that object's mass times G. Now this is a single variable G. This is an actual amount in the formula G. This G right here, I'm actually going to make it smaller. This is not its own variable. This G is a subscript of F. It's attached. It's not a separate thing that you're multiplying. But this G here is a separate thing that you are multiplying. This G represents the acceleration due to gravity. All objects on Earth are going to have different weights based on their mass, but all objects on Earth are going to accelerate down due to gravity at the same rate. All objects on Earth's surface fall at the same rate. There's been lots of experiments in the past where someone has dropped a very small golf ball at the same time as they've dropped a bowling ball. Those have very different masses, and yet they fall at the same rate. They're both going to hit the ground at the same time. The actual mass of the object does not affect the acceleration of the object. Every object is going to accelerate at the same rate down. That same acceleration being multiplied by every object's different mass is what gives us the different force of gravity, the different weight of every possible object. And since every object falls at the same acceleration, we know what that acceleration is. So every time you see G, the value of G is negative 9.8 meters per second squared. This is the acceleration due to gravity on planet Earth. Wherever there is a variable G in a formula, this number is what you plug in there. This is a free number that you always know. This is acceleration due to gravity on planet Earth. This is a constant. And you can write this in on your formula sheet if I didn't put it there myself. This is a known thing. This is a freebie for you. So, to find the force of gravity on anything, you just multiply its mass in kilograms, mass in kilograms, times 9.8. And the negative sign just means down. The negative means that this force is pointing downwards. That is all it represents. So, this formula here is just a slight variation of Newton's second law. All of these things we talked about so far have tied into Newton's laws, and in a second we're going to utilize those laws to move on to an additional topic. Okay, so moving on to our next topic and moving on to slide number 6. First, on slide 6, we are introducing the concept of work. Now, you've all done work before, both literally in terms of physics and also literally in terms of school. Now, the physics definition of work, which we are going to talk about now, is when you use energy, when you use or transfer energy from one object into another. And you know that you are doing, this is the physics definition of work, you know that you are doing work when you exert a force on an object and that object begins moving in the same direction that you are exerting the force in. So I'm going to push this chair forwards, it's going to move forwards, and according to physics that means I have done work on my chair. So, according to Newton's second law, when you exert a force on an object, if that force is imbalanced, that object may begin accelerating. If that object is accelerating, it's going to travel it's going to begin displacing in that direction. And if you exert that force while the object is displacing, You have done work on the object. So, anytime you have ever moved something in your life, when you exert a force to cause something to move a distance, you have done work. And so, what that means is, when you are writing, like when you just take a pen or pencil or marker, and you are physically writing with it, you're exerting a force to move the marker around. It's moving a distance as you exert force on it. So, when you are doing your homework, you are literally doing work in terms of physics. And if your family ever gets onto you for not doing your work, just say, I've done work today, because anytime you pick up or move something, you've done work. So keep that one in your back pocket. Now moving on to slide 7, this is going to be the formula for how you find the amount of work that you have performed. The formula for work is the W right here. So this variable here is work. And the work that you do on an object is equal to the force you apply to an object times the distance the object travels. So, work equals force times displacement. The more force you exert on an object, the more work you are doing. Which, if you've ever, you've all lifted something heavy before. The heavier something is, the more force you have to exert in order to lift it, the more work that you have done. You have used up more work, you've used more energy, done more work to accomplish that task. Additionally, the farther you push something, if the displacement gets bigger, if this is a bigger number, that is also going to increase your work. So the farther you push something, the more work you have done, even if it's a small amount of force. So, anytime you exert a force and something moves a distance because of that force, you have done work. Now, I'm going to explain this little p right here. This is another subscript, so this is force sub p. We're not multiplying force by p. This is specifically force with this subscript attached. This is all one variable right here. And what that p represents is parallel. That p tells us that this force has to be parallel to the displacement. And the definition of parallel means in parallel axes, the same axis. So, let's say I have a box and I am going to exert a force on it in the horizontal axis. So this arrow here represents an applied force of 50 newtons. If I was pushing this box to the left and the box begins moving towards the left, these two arrows are parallel. They're in the same direction. And because they are parallel, if I exert 50 newtons of force and the box slides 1 meter, they're in the same direction. These are fine variables to plug into our formula here. These two things are parallel to one another, so they are safe to plug into the formula. The issue arises if a force is not parallel to the direction an object is traveling in. So let's say, even though I'm pushing the box to the left, for some reason the box is sliding downwards. This direction is not parallel to this one. These are perpendicular to one another. Because they are not parallel, the amount of parallel force to this direction is actually 0. I am exerting 0 newtons in this direction. All of my force is to the left, and that's not accomplishing anything because the box is not moving to the left, it's moving down. I'm not exerting any force in this axis, so the parallel force, the force that is parallel to this direction, is actually 0. So in this scenario, where I'm pushing the box, where my force points to the left, but the box is moving downwards, even though I am exerting a force and the box is moving, I'm not actually doing any work because I'm not doing this. There's no way I can push this box to the left and it slides down. Something else is doing this, and it's not me. Something else is doing work here, and whatever I'm doing is not accomplishing anything. So when I say that, you know, whoever's exerting this force is not doing work, it means they are not causing the movement. So this is going to be our formula for work that we are going to use. The W here represents the work itself. Something to be aware of, work is measured in units of joules. So we measure distance in meters, we measure mass in grams, we measure force in newtons, and we measure work in joules. Joules is the metric unit for energy, because when you do work, you are using up energy. When you lift that heavy object, you have used up the energy in your muscles. So when you do work, you are using energy. That's why the unit of work is the same as the unit for energy. So now we're going to move on to slide number 8, and we're going to utilize this a little bit. So I'm going to modify this picture just a little bit. I am pushing a box across the floor. I exert a force of 50 newtons on the box, and it slides 10 meters in the same direction. So this is the force I apply. This is the distance the box slides. These two directions are parallel to one another. They are in the same axis. So question 1 asks, how much work am I doing pushing this box? So our formula is work equals force parallel times displacement. I'm doing a force of 50 newtons that is parallel to our displacement of 10 meters. Therefore, in this act, I am doing 500 joules worth of, I am doing 500 joules worth of work. That is the work that I am doing on this box right now. The next part of the slide asks what amount of work that gravity is doing. So we're going to use the numbers that the slide gives us to try to find how much work gravity is doing. Now, the slide tells us that gravity is exerting a force on this box. The weight of this box and the weight of an object is the force of gravity. So, the box weighs 100 newtons. The force of gravity is going to be 100 newtons. But keep in mind that 100 newtons is pointed down, so it has a negative sign on it. So, this is the force of gravity on the box. This is its weight. So, if we want the work done by gravity, we have to plug in the force of gravity. So, want to find work, we're going to plug in our force of negative 100. Now, the box is sliding to the left in the x-axis. It is not moving down. It is not moving parallel to this force. So, you can either look at it as this force is not parallel to this direction, meaning that the actual force of gravity that is parallel here is 0. You can also think of it as the box is not sliding down. The distance traveled downwards is 0. So one way or the other, one of the numbers you plug in here is going to be 0. Either you're going to multiply 0 by negative 100, or you're going to multiply 10 by 0. Either way you look at it, depending on whether you think this is the distance and there's no force parallel to it, or this is the force and there's no displacement parallel to it. Either way, you're multiplying by 0, and the answer you're going to get for the work done by gravity in this particular example is 0. Gravity is not doing any work on this box because this box is sliding to the left. It is not sliding in any direction parallel to the force of gravity. And that is your introduction to work. Pretty straightforward formula. Now, when you do work, you use energy. You are using the energy in your muscles and transferring that energy into another object. If I exert a force, if I do work on this chair, I am using my own energy and giving it to the chair. And when the chair has energy, it moves. Work is measured in the same units as energy because you use energy to do work. What we're going to move on to next, our next topic, we're going to look at some of the types of energy that you can create, that you can give to objects when you do work on them. So, if you move on to slide 9 sort of summarizes what I've already just said. When you do work, you are giving energy to the object. And we're going to now learn about two different types of energy. These will be the two types of energy we're studying most in this class. The first one, and the one that's going to be on slide 10, move on to slide 10, is kinetic energy. Kinetic energy is the energy of movement. If an object has kinetic energy, it means that that object is moving. So when I move my eraser across the board, I'm exerting a force on the eraser. I'm making it move a distance in a direction. I'm doing work on the eraser. And since I am making it move, since it now has a velocity, I have given it kinetic energy. I have used up energy in my arm and done work to give that energy to the eraser to make it move. And if an object is moving, that means it has some amount of kinetic energy. And our formula for kinetic energy, we're going to shorten kinetic energy as a variable down to Ke. So anywhere you see a Ke, that's going to represent the kinetic energy itself. The kinetic energy an object has is going to be equal to 1/2 times that object's mass times its velocity squared. So if an object has mass, and all objects do, and it has a velocity, so if it is an object that is moving, if it is currently moving at some velocity, that object is going to have some amount of kinetic energy. So if I throw a marker into the air, I do work, exert a force on the object and make it move a distance. I am taking the mass of this marker and giving it energy. It now has a velocity because I have given it kinetic energy. So, let's use this formula in a quick example. Moving on to slide 11. We have two separate objects listed here. They each have a different mass and a different velocity. We're going to compare the two to see which one has more kinetic energy. So, we're going to start with object A. Kinetic energy is equal to 1/2 times mass times velocity squared. Object A is a 5,000 gram bowling ball that is rolling at 3 meters per second. Now, whenever you see an M in one of our formulas, we're going to want kilograms, not grams. And 5,000 grams is equal to 5 kilograms. 5,000 grams becomes 5 kilograms. So the number I'm going to plug in for the mass of the bowling ball is 5 kilograms. And that 5 kilogram bowling ball is rolling at 3 meters per second. Our velocity term is squared, so we're going to square that 3. That means the kinetic energy of the bowling ball, I'm going to pull out my calculator and show you how I enter this. We've got 1/2 times 5 times 3 squared. So what I've got in my... Pardon me, everybody. Calculator slipped out of its case. Excuse me. So what I've entered here is 0.5 times 5 times, and I've done open parentheses, 3 raised to the second power, closed parentheses. You want to make sure that it is putting the squared on only the 3. So I have put parentheses around the 3 squared to make sure it is only squaring the 3. And if you press enter, that'll give you that this bowling ball has 22.5 joules worth of kinetic energy. The second object is a person. This person has a mass of 100, sorry, went a little out of order. KE equals 1/2 times. This person has a mass of 100 kilograms. That's already in kilograms, so we can plug in the 100. And this person is walking at a velocity of 1 meter per second squared. So, 1 squared is going to be 1. So this whole thing just becomes a 1. 1 times 100 is 100. 100 times half is going to be 50. So the kinetic energy of this walking human is 50 joules. So, the human, the walking person, even though they are moving at a lower velocity, the ball was rolling at 3 meters per second, the human is walking at 1 meter per second. The human had more kinetic energy because they had a much bigger mass. The more mass something has, the more energy it needs to be moving at a certain velocity. It takes a lot of energy to make massive, meaning has a lot of mass, objects moving. But that is some practice with the kinetic energy formula. So kinetic energy is the energy an object has when it is moving. There's one more type of energy we're going to discuss. So now moving on to slide number 12. The next type of energy is called gravitational potential energy. Now, in the past, and in some classes you've hopefully heard of potential energy. When an object has potential energy, that is energy that is stored in an object. Whereas kinetic energy is in use, making an object move, potential energy is energy that is stored away. It's waiting to be used. It's very similar to a battery. A battery, like in your phone or your laptop, has stored energy inside of it waiting to be used. And when you plug the battery in, that potential energy is converted into some other type of energy to power the device. Now a battery has electrical potential energy. What we're going to talk about here is gravitational potential energy. And rather than, it is still stored energy. It is energy stored in an object's ability to fall. So right now, this marker could be falling. It could fall all of about 2 meters until it hits the floor. It isn't right now, but it has a bunch of energy stored up inside of itself to use when it starts falling. I'm holding it in place at this height right now, So all of that energy is currently stored within it. Once it is allowed to fall, that energy is going to be released and transform into kinetic energy, because after it begins falling, it now has a velocity. So whenever you lift an object upwards, you are giving it, you are doing work to give that object gravitational potential energy. I have elevated this marker to a point where it has energy stored in its ability to fall, and when it falls, that energy is going to be released. And the formula for gravitational potential energy, we shorten that to GPE. That formula is going to be equal to mass times G, which is 9.8, times height. The gravitational potential energy of an object is equal to its mass times 9.8 times its height above the ground. The more mass an object has, the more work you need to do to lift it. If something has 3 times as much mass, you have to do 3 times as much work to lift it up to a certain point. You had to do more work to get it there. That means it has more energy stored inside of itself. You've put more energy into it to elevate it. Also, the higher you lift something, if H goes up, that means the object is going to have more GPE as well. Because the higher I lift it, it now has more potential to fall even further and to reach a higher velocity before it hits the ground. So the higher something is, the even more GPE it's going to have. So, if we move on to slide 13, let's practice using these formulas now. We have another pair of objects listed together, and we're going to see which one has more GPE. First, object A. We have a 5,000 gram object being lifted upwards by 10 meters. So, the GPE of this object is equal to its mass. Keep in mind, we want to use grams. I misspoke. We want to use kilograms, not grams. We want to use kilograms. And 5,000 grams becomes 5 kilograms. So, 5 kilograms times 9.8, that's our acceleration due to gravity. Wherever you see a little g, you can plug 9.8 in for it. That 5 kilogram object has been lifted by 10 meters. So, the GPE of this object is going to be 5 times 9.8 times 100. We're going to pop that into our calculators. 5 times 9.8 times 10. And that tells us this object, when it was lifted, has a GPE of 490 joules. Object 2, object B in this example, is a 100 kilogram object that has been lifted by 10 centimeters. So our mass, 100 kilograms, it's already in kilograms, so that's good, we don't have to convert it, times 9.8 times our height. This box has been lifted by 10 centimeters. We want to use meters for all of our standard lengths. That means we need to convert centimeters to meters. By definition, 1 meter is equal to 100 centimeters. That's a conversion that you should keep. That means if I'm going to convert our 10 centimeters, I'm going to take 10 centimeters, 100 centimeters equals 1 meter. Cancel our units. 10 divided by 100 means that this is going to be 0.1 meter. We have lifted this box by 0.1 meter. Multiply all those together to get our final answer. And that tells us that this object has 98 joules worth of gravitational potential energy. 98 joules. So, object A has more GPE in this scenario. It was lifted much, much higher, even though it has a lower mass. And these are the two, so therefore, in conclusion, these are the two types of energy we have talked about so far. Kinetic energy is what an object has if it is moving at some velocity. GPE is what an object has if it is some height above the ground and it's remaining there. And in order to give objects these types of energies, we had to perform work on it. When we did work, we were giving the object these types of energies. And that is our work and energy topics. So in a second, we're going to talk about power. Okay, so jumping right off from work, the next thing we're going to talk about is power. Now, we're using physics to define these things. We gave the physics definition for work. Now we're going to give the physics definition for power. When you push an object in a direction, so I'm exerting a force and this chair is going to move a certain distance in the same direction, I am doing work. I'm using up energy. Now, power is defined as, if you move on to slide 14, power is defined as the rate at which work is done, the rate at which energy is used. So, if I use our work formula here, if I push this chair a certain force in a certain distance in a direction, and we do the math, I know the force I exerted, I know how far I push it, that math will tell me how much energy I used during that total process. But that doesn't tell you when I got there. It doesn't tell you the rate at which I am using energy. I could be exerting that force over a very short period of time. I could jet right over there with my chair, or I could do it very slowly. This formula does not tell you the amount of time that it takes. It doesn't tell you the rate at which your energy is used up. That is what power is for. Power is the rate at which energy is used. So if you do a task quickly, you use a lot of energy in a very short amount of time. That means you used a lot of power. If it takes you longer to accomplish a task, you could be using the same amount of energy in that time, but, if it takes you longer to accomplish a task, it might take you the same amount of energy, but if it takes a longer amount of time, you aren't as powerful. You weren't using as much power. Now, power, we measure power in units of watts. You've all seen, I presume you have seen the unit watt used before. It's commonly used to refer to like the wattage of an appliance or a light bulb. So say you have a 60-watt light bulb. That means every single second, 1 watt means you need to use 1 joule per second to power that device. 1 watt, if you have 1 watt of power, you're using 1 joule every second. A 60-watt light bulb needs 60 joules every second to stay on. If it doesn't get that much energy, if it doesn't get 60 joules in 1 second, that light bulb will go dim and eventually it will go out. So power is energy in an amount of time. And it is measured in watts. And when you shorten watts, it is shortened to a W. I want to help avoid confusion between this W and this W. This is a variable in a formula. This is the formula right here. There's no units in the formula, just variables. And when you see W as a variable in the formula, it means work. If W is used as a unit, then it's watts. power. I want to just make that important distinction. There's going to be two formulas for power that we can utilize. The first one says that power is equal to work divided by the time. This is, you do a certain amount of work in a certain amount of time. And that tells you how powerful you were. If you do more work in the same amount of time, that's more power. If you do the same amount of work in less time, that's more power. There's an additional formula that you have access to that may help with certain questions. And that is power is equal to the force applied to an object that is parallel to that object's constant velocity. So these are separate formulas, but they can both be used to find power. And this formula here is, I think, best exemplified when you have a car active and you have your cruise control activated. When your car's cruise control is activated, it has a computer that is automating the engine process for you, and so that the car stays moving at constant velocity. In order to do that, the engine has to exert a certain amount of force on the wheels. The engine is exerting a force to propel you forwards. So your car is moving at a constant velocity due to an applied force from the engine. Those two things multiplied together would tell you the power of your engine, or the power output that the engine is currently giving out. And watts is the metric unit for power, but the term horsepower is a different unit for power. Like how feet and meters both measure distance, both watts and horsepower can measure power. So on car commercials where they talk about the horsepower of a car, it is the literal power of the car, how much energy can it use in a certain amount of time, etc. So, that's what power is. We're going to utilize these concepts in a sample question. If you move on to slide 15. So, two people are both carrying boxes up a flight of stairs. So this is going to represent our flight of stairs. And this stair flight has a total height. Sorry, rereading my own slides. These stairs have a height of 10 meters. They're 10 meters tall. Two separate people are going to be climbing these stairs. One of them, person one, person one is carrying a 3 kilo. Gotta reread my own slides before I say anything. Is carrying a 3 kilogram box, and it takes person one 1 minute to climb these stairs. So this person is carrying this 3 kilogram box all the way up these 10 meters, all the way up, and it takes them 1 minute to do this. The other person, person two, has a 2 kilogram box, and it takes them half of a minute to get up these stairs. So they're both going to climb the same distance, but they're carrying different mass boxes, and they're making it up there in different amounts of time. So, we've read the question, we've drawn our pictures, we've been listing our variables, so now let's start working on the problem. The first thing we were asked is, which person does more work? So the first thing we need to do is find how much work each person is doing. Now, these boxes are being lifted 10 meters vertically upwards. We are lifting upwards. So if we're going to use our work formula to find the work done by each person, we know the distance upwards they're being lifted, so we need to figure out how much force upwards, because this has to be parallel in the same axis, how much force upwards it took to lift each of these boxes. And in general, the force it takes to lift an object right upwards is its weight. The force of gravity is what you have to overcome to lift something. So, the way that you find the force of gravity on any object is by multiplying its mass times 9.8. So, this is the force we can plug in for force parallel. This is the distance upwards. So, we are exerting a force upwards equal to weight. In order to overcome that weight, we have to exert at least this much force to lift the box. We are exerting that force upwards in the same axis as this 10 meters upwards. So, for each person, this is going to be work 1 in green. We want the force parallel 1 times x. The force exerted is going to be equal to the box's mass, 3 kilograms, times 9.8. So, we've plugged in mg for force because this is the force you would have to lift upwards. In order to lift anything upwards, you have to exert a force equal or greater than its weight. And then we multiply by the distance. So, person 1 is going to do $294 joules worth of work. Now for person 2. So we got work 2 is going to equal force parallel 2 times x. It's going to look very similar, except person 2's box had a mass of 2 kilograms instead of 3. So we plug in a 2 instead of a 3. And that tells us that it took this person 196 joules worth of work to lift this box all the way up these stairs. So, person 1 did more work. That's the answer to the first part. The second part asks, which person had a better power output? Which person used more power? So, for each person, we know how much work they've done. We know the time it took them to climb the stairs, and we want their power output. And this formula here tells us power equals work over time. So this is going to be the formula we're going to want to use. So the power performed by person 1 is going to equal their work over their time. So, person 1 did 294 joules worth of work, and it took them 1 minute to climb these stairs. Now, just like how we want to use kilograms for mass and meters for distance, there is a specific unit we prefer to plug in for time in all of our formulas, and that is seconds. So we can't plug in 1 minute, we have to plug in seconds. So there are 60 seconds in 1 minute. So instead of dividing by 1, we're dividing by 60. Important note. So 294 divided by 60 tells us that person 1 had a power output of 4.9 watts. 4.9 watts. We're going to do the same thing with person 2 now. So person 2, we want their power output. That's going to equal their work done over the time it took them to climb those stairs. So, person 2 did 196 joules worth of work, and it took them half a minute to climb the stairs. If 1 minute is 60 seconds, half of a minute is going to be 30 seconds. So we're going to divide by 30. 196 divided by 30 is going to tell us 6.53 watts of power. So, Person 2 had a better power output. Person 1 did more work, but person 2 did their work faster. That means they output more power. They exerted their energy. They did their work more quickly, which represents that they had a larger power output. So, someone can do more work, but that doesn't necessarily mean that they had the most power. Important thing to note. So, talked about power. We have our formulas. We've done an example. We're going to move on to another topic now, and that is the science behind friction. Okay, so next concept is friction and how it applies to some of the other concepts we've already talked about. Now, friction is everywhere because it happens whenever any two objects physically touching one another slide across one another. Every single surface in the universe is rough on some atomic level. If you zoom in far enough with a magic microscope, if you zoom in far enough, even the smoothest object is going to have ridges and bumps and cracks on it. And since every single object has these ridges, whenever any two objects touch, those two ridges are going to get stuck inside one another. And as a result, they tend to get stuck. It's hard to push these two objects across each other. It's hard to slide them across each other when they're stuck like this. And so friction is a result of this phenomena that results in it being hard for two objects to slide across one another. And this happens when any two objects touch. You can feel it when you rub your own palms across each other. All of that heat that you feel as your palms warm up is friction working against your movement, taking energy away and making your palms warmer. It happens whenever any object slides across the tabletop. Friction will exert a force on that object to try to slow it down. For example, if I roll this marker across the table, it's eventually going to stop. Oops. It would help if I had a better desk. But if I push this marker forwards, there's friction between the marker and the table. The surface of the marker is, being rough against the surface of the table. And so as the marker is trying to move forwards, the friction is working in the opposite direction. So friction opposes movement. The marker's trying to move this way, but friction is going to point in the opposite direction to try to stop it, to slow it down. So once I'm no longer touching the marker, the force of friction is going to push it this way. That means that it's going to begin accelerating this way. That means it's going to slow down. If its velocity is this way, but it's accelerating this way, it's going to slow down until it stops. Once it stops, there's no more motion to oppose. The friction is going to turn off. So all friction comes from any two surfaces interacting in such a way. And actually this can even include air, because air is an object, and if you move your hand through the air, you can feel the force it exerts on you. You can feel the air friction. Friction is everywhere in our real world because everything is always touching something. Even if you're flying, you're touching air. And so there's friction literally all around us. We can't really get rid of it, so we do have to understand what it is and why it's there to be able to factor it into our math and work around it. So slide 16 summarizes this about friction, all this information. Slide 17 shows the formula for friction, which I've already got on the board and we're going to talk about now. So that F sub F, the big F with the little f next to it, this is force of friction, and we find the force of friction by multiplying the normal force acting on an object times, this is not an M, this is not an M. I'm actually going to adjust it really quickly to make it less like an M. And this marker's dead. This is the Greek letter mu. This is a Greek letter. We pronounce this letter as mu. We don't have a fraternity on campus with a mu in it, to my knowledge, but we do have one with a nu in it. So mu is kind of like the M to nu's N. So this is a Greek letter, mu, and it represents the coefficient of friction. And this is important because every object is different. Every object has a different surface texture. It's going to have different bumps and ridges and cracks on it. And that means they're all going to have different frictions as compared to one another. You're going to have a different amount of friction if I slide my hand across this smooth board than if I was to slide my hand across sandpaper. Sandpaper is very rough. This board is very smooth. So there's going to be different amounts of friction there. Mu, this coefficient, represents that. The smoother something is, the less friction it's going to produce. And therefore, that object is going to have a smaller mu. The mu represents how much friction that object creates. If an object is really rough, really bumpy, it's going to have a higher mu, and then it's going to create more friction. Now, the coefficient of friction doesn't have any units. It's a unitless number, meaning you never attach anything like newtons or meters to it. It is unitless. And it's always going to be between 0 and 1. It's never going to be smaller than 0. It's never going to be bigger than 1. It's always going to be a very small decimal. So it has no units, and it will always be a small decimal number between 0 and 1. So this represents the surfaces involved in creating the friction. This tells you how slick the surface is. The N is a different principle called normal force. And normal force is summarized on slide 18. Normal force is the force a surface exerts out of itself when you exert a force into it. So, flashback to Newton's third law. When I lean into the board exerts a force back on me. That force coming out of the board is the normal force. The board is exerting a normal force on me, holding me up. It's the force that the surface is exerting into me. And it's the same principle when my chair is sitting still on the floor. Gravity is pulling the chair down, so the chair is exerting a force down into the floor. But the chair is not falling through the floor because the floor is exerting an equal and opposite force back up into the chair. The surface of the floor is exerting a normal force upwards. So, normal forces are created by surfaces as a result of having a force act into them. The force from the chair is pushing down into the floor, therefore the floor is going to push up into the chair. And the reason this matters for friction is because if I lean against the board, if I push into the board is going to push into me. And the more the board pushes into me, the more friction there's going to be. Take your hands, slide them back. Okay, rewind a sec. Take your hands, hold them very gently against one another. barely have them against one another. Just have them barely touching. And begin rubbing them across one another. You can feel the friction. You can feel a little bit of heat being generated, but it's not much. That's because you're not pressing your palms very hard together. Your palms are not pressing into each other very much. Therefore, there's not much normal force between your palms. But if you press harder into your palms, if one palm pushes harder into the second, and therefore the second pushes harder into the first, and then you try to rub them across one another, there's a lot more friction there. You are pushing the bumps and cracks harder into one another, so it becomes harder to slide those two surfaces across one another. So, the two things that affect the friction between two objects are the normal force between the objects and how smooth they are, the coefficient of friction of those objects. So, friction opposes movement. We're now going to utilize this formula and a few others in an example question on slide 19. This question involves a horse and buggy. So I'm going to read the question, I'm going to draw pictures and list variables as we go. A buggy is being pulled down the road by a horse, and the horse is pulling on the buggy forwards with a constant force of 65 newtons. The buggy has a mass of 150 kilograms. So, we know the force being applied forwards on the buggy. The horse is pulling it forwards with this mass, and with this force, and this is the mass of the buggy. Question 1. Why doesn't the buggy get faster and faster? The horse is pulling it forwards. This force is pulling this mass forwards. And we know if you exert a force on a mass, it should accelerate. So if the buggy is moving at constant velocity, why is the buggy moving at constant velocity? Why is it not continuously accelerating forwards as it's being pulled forwards? And the reason is friction. The horse is pulling the buggy forwards, but friction between the buggy and the ground is pushing backwards. These two forces are opposing one another. When you're driving your car and you turn cruise control on and you want your car to move forwards at a nice constant velocity, what your car's computer is doing is it's calculating how much force it needs to exert to counteract the friction from the road and keep you moving at constant velocity. So when you turn cruise control on, your car exerts just enough force forwards to counteract an equal and opposite amount of friction backwards. If you're moving at constant velocity, you have to exert a force forwards equal but in the opposite direction as the friction pushing you backwards in order to maintain constant velocity. If the two forces are not balanced, you'll begin to accelerate. But as long as they are balanced, they're pointing in opposite directions, as long as they're balanced, they will add up to 0. If the force equals 0, the acceleration equals 0. That is part A. Part B asks, what is the weight of this buggy? What is its weight? And simple answer is, the way that you find the weight of any object, the weight is the force of gravity. You multiply its mass by 9.8. So, buggy has a mass of 150 kilograms. You multiply that by 9.8, which is the acceleration due to gravity. And that will tell you the force of gravity, the actual force that gravity pulls down on it with, in newtons. So, the buggy has a total weight of 1,470 newtons. I should note that this force is downwards. Gravity pulls down. The next question, C. Let's identify all of the forces acting on the horse. Let's identify all of the forces on the horse. So this is going to be our poorly drawn horse. Very poorly drawn horse. Fun fact, physicists cannot draw. Most of them cannot draw. I'm sure there's some who can, but most of us can't. So this is our poorly drawn horse. Let's examine all the forces that are acting on this force. Forces acting on this horse. So, gravity is going to pull down on all objects. Gravity is always going to pull down on everything. But as this horse trots along on the road, is the horse falling downwards? No. That means there's something pushing the horse upwards, keeping it from falling into the earth. And that is going to be normal force from the ground. The ground is going to push up on the horse to keep it from falling into the earth. And we know, since the horse is not accelerating up or down, it's not rising or falling, that its vertical forces must add up to 0. So the normal force and the force of gravity must be equal and opposite in order for this horse to be moving only horizontally. Next, the horse has to push itself forwards. It has to be applying some force to pull itself and the wagon forwards. Meanwhile, there's some force of friction on the horse pulling it backwards. If the horse is moving forwards at constant velocity, then the force forwards and the force backwards have to add up to 0. You can move at constant velocity. If you're moving at constant velocity, you're not accelerating. If you're not accelerating, all the forces acting on you must be equal. So, the horse is exerting some force forwards to move forwards. That is equal and opposite to the force of friction slowing it down. Gravity is pulling the horse downwards. That has to be equal and opposite to the normal force holding it upwards. All of these things have to be equal within their own axes for the horse to be moving at constant velocity. So these are the 4 forces currently acting upon the horse. The last question, D asks, what is the coefficient of friction between the horse and buggy and the road? So, we want coefficient of friction. That's this thing. We want mu. And we only know one formula with mu in it, so this needs to be the formula we're solving for. We know this is the formula that we are about to look at. Force of friction is equal to N, normal force, times mu. So we want mu. That means we need to find a normal force and a force of friction to plug into this formula. Now, the horse and the buggy are both moving only horizontally. They are not accelerating up or down. That means, as a general rule, if an object is just sitting on a horizontal surface or moving sideways horizontally at constant velocity across a horizontal surface, it's not moving or accelerating up or down. That means normal force and gravity need to be equal and opposite. We know the weight of the buggy. Gravity pulls down with this much force on the buggy. But we know that the normal force must be 140 newtons upwards to counteract that gravity and keep the buggy from falling into the earth. So we can plug this number in for our normal force, because the force of gravity and the normal force have to be equal but opposite to one another. So the normal force on the buggy would have to be 1,470 newtons upwards. It would have to be. And that's a number we can plug in for N. Next, the force of friction on the buggy. Well, let's look at the buggy itself again. The buggy is moving forwards at constant velocity. That means all of the horizontal forces on the buggy must be equal and opposite. the only force pulling the buggy forwards is the 65 newtons from the horse, and the only force pulling it backwards is the force of friction. Therefore, in order for the horizontal forces to add up to 0, these two things, the horse force and the force of friction, must be equal and opposite. So the force of friction is going to be 65 newtons backwards. That means we have a number we can plug in for force of friction and for normal force. Even though the problem didn't tell us normal force and force of friction, we can still find them using what we know about Newton's laws. So we know our force of friction has to be equal to 65 newtons, and we know our normal force has to be equal to 1,470 newtons. And we want to solve for mu. So now I just need to divide both sides by 1,470, and that will tell us mu. So 65 divided by 1,470, and that's going to tell us that the coefficient of friction between the buggy and the ground is 0.044. Again, mu does not have any units. There are no units to write here. You don't write meters, you don't write newtons, it's just blank. And like I said earlier, this is a very small integer number between 0 and 1. So, this answer makes sense. We have examined all of the forces, including friction, acting upon this system. Well done, everybody. That concludes the notes that concludes the friction part of the notes. We're now going to move on to the next topic. Okay, our last topic for today is momentum. Now, this is something that you have interacted with definitely before in your lives. You've definitely heard the word before. In the common English vernacular, we're familiar with the idea of building up momentum. And this does tie into the physics definition of momentum. An object that has momentum is harder to stop. It takes more effort to stop an object that has a lot of momentum. The more momentum something has, the harder it is to stop, which falls in line with sort of the colloquial version that we talk about, where we say, you know, we want to build up momentum, we want to keep this going, we want to make our effort harder to stop. And physics is the same way. Now, the way that we find momentum in physics is something an item can have. It's sort of like energy. Energy is this substance, this not even really a substance, it's this quantity that an object can possess that lets it do stuff. Similarly, momentum is this quantity that objects can possess. An object has to have momentum. You cannot have momentum without it being in an object. An object with momentum needs to have mass, and it needs to be moving. If an object is completely stationary, then it has no momentum. None. It hasn't built up any momentum, it's not moving. It's very easy to stop because it's already stopped. I don't have to do anything to it. In order for something to have momentum, it needs to be moving. Once an object with mass is moving, when an object with mass has a velocity, it then has momentum. Now, we're going to look at slide 20, has this information and the formula for momentum on it. We're going to look at that formula now. Momentum. The thing about physics equations is we've been doing physics for thousands of years, and in that time we sort of ran out of letters that made sense for our variables. So the variable for momentum is not a large M. It's not any kind of M. It's actually this letter here. It looks like a P, but it's actually not a P. It's the lowercase Greek letter rho. So this right here, this letter here, this blue marker is running out of ink. That letter there is the Greek letter rho, and that represents momentum. This is the variable form of momentum. And you find the momentum of an object simply by multiplying that object's mass in kilograms by that object's velocity in meters per second. All you do to find momentum is you multiply those two numbers. An object that has more mass will have more momentum. An object that is moving faster will have more momentum. Both of those things contribute to an object being easier or more difficult to stop. If a large object, imagine an Indiana Jones movie, and you've tripped a trap and there's a boulder rolling towards you. That boulder has a lot of mass and a lot of velocity. That means it's going to have a lot of momentum and it's going to be very hard to stop. So there's no way Indiana Jones can reasonably actually push the boulder to stop it. There's no way he can do that. It's going to take too much effort, so he's much better off running. But if the boulder had a very low mass and or was moving very slowly, it would have a lot less momentum and he could probably stop it. We're going to test that now by looking at slide 21. Slide 21 proposes 4 different scenarios. There are 4 different objects listed on slide 21, and they each have 4 different velocities. We're going to examine them now to determine which one has the most momentum. Object A is a building, and this building has a huge mass of 100,000 kilograms. So the momentum for object A, this building, is its mass, 100,000, times its velocity. But the thing about buildings is they tend to be stationary. Buildings don't usually have a velocity because they're rooted to the ground. So this building, this stationary means not moving, its velocity is 0. Therefore 0, even times this huge mass, is going to be 0. So this building, object A, has a momentum of 0. And the unit for momentum, we actually don't have a dedicated unit for momentum. Force has newtons, distance has meters. Momentum does not have its own special unit. Since we are multiplying mass by velocity, the unit for momentum is just kilograms times meters per second. It's a little bit of a mouthful, but you don't have to remember a new symbol at least. So, if you have no velocity, you will have no momentum. So, this building is easy to stop because it's already stopped. Next, the second object, a 10-gram bullet fired at a velocity of 1,000 meters per second. So, 1,000 meters per second is a very big velocity, but bullets are very small. They don't have a whole lot of mass to them. And the problem tells us that this bullet has a mass of 10 grams. All of our formulas are going to accept kilograms. So we need to convert the 10 grams to kilograms first. Now the rule is 1 kilogram is equal to 1,000 grams. Therefore, 10 grams, and this is the way that I've been doing all of my conversions for this class. If you have a different way that you like to do your conversions, that is fine. I don't want to confuse you by saying this is the only way to do conversions. If you have your own method that works for you, by all means, please continue. I just this is how I set mine up. So I've got grams, this is my conversion. I put the grams in the conversion on the bottom, kilograms at the top, and that tells me that the mass of this bullet in kilograms is 0.01. So that is the bullet's mass in kilograms. That has to be the mass that I plug in here. So 0.01 times 1,000 is going to be 10 kilogram meters per second for the bullet. Next, we have a 25 kilogram dog running at 10 meters per second. Both of those are already in our standard units. We have 25 kilograms and 10 meters per second. We don't have to adjust anything. We can pop both of those numbers into our formula. So this dog is running with 250 kilogram meters per second. That is more than the bullet. Last one, we have a car. Cars have a lot of mass, 2,000 kilograms for this one car. And it's driving forwards at 1 centimeter per second, which is very, very, very slow. This car is idling. Whoever is driving this car has only just barely tapped the gas. You are inching forwards incredibly slowly. Now, again, our formulas want meters per second. So, the conversion here is 1 meter is 100 centimeters. Therefore, 1 centimeter per 1 second. We want to convert the centimeters to meters. So 100 centimeters is 1 meter. Centimeters cancel. That's going to leave us with meters per second. So our meters per second here is 0.01 meters per second. 0.01. So that's the number we're going to plug in for the velocity of the car. And that's going to tell us that the car has a total momentum of 20 kilogram meters per second. So out of all of these objects, the one with the most momentum, and therefore the hardest object to stop, is actually the dog. Not the truck and not the bullet. Now, this bullet would hurt. Not saying it wouldn't. This is just very slow, and this is actually probably a lower mass than most actual conventional bullets. So most bullets would have more momentum than this, I think. But for the sake of this example, the dog has more. The dog has most momentum out of everything listed on this slide. So that is a little bit of practice for the momentum formula. Again, momentum is a measure of how hard it is to stop something in motion. If you go to the next slide, there's going to be one more concept we're going to mention today. And it's nothing to worry about. It has a name, it has its own symbol, but it is not any more complicated than momentum, because the new concept is impulse, and the definition of impulse is change in momentum. The definition of impulse is change in momentum. If the momentum of an object changes due to it starting at rest and then being forced to move forwards, or if it was moving and then it slows down for some reason, then that object has undergone an impulse. Impulse just means change in momentum. That's all it means. If an object's momentum changes due to its velocity changing, then it has undergone an impulse. And again, physics ran out of letters that made sense a while ago, so the variable for impulse is J. The way that I like to remember it is, rho stands for momentum, so rho-mentum. J stands for impulse, which I remember as Jimpulse. But that's just because my brain makes those puns all the time. Now, because impulse is just the change in momentum, it is also measured in kilogram meters per second. It's just the change in momentum, so it has the same units. It is just if the object's momentum changed. Now, there are two other formulas that you can use to find impulse. I'm just going to list them on the board so that you have access to them. One of those formulas is force times time. If you exert a force on an object for a certain amount of time, that is going to change the object's momentum. Additionally, one way to change an object's momentum is to change its velocity. So if you multiply the object's mass by the change in its velocity, that will tell you the object's impulse, the change in its momentum. So that is all that the impulse represents. We're going to utilize this in one more example slide for this set of notes. Just one more. The last slide of this notes, slide 23. Baseball is an excellent example of impulse because the whole point of the game is the ball is initially traveling forwards at some specific velocity, and in this particular case, this fastball has a mass of 145 grams, and its initial velocity is 44.7 meters per second, which is very fast. This is a very good pitcher. The ball is initially moving forwards towards the batter at this velocity. And the entire point of baseball is for the batter to strike the ball and change its velocity. You want it to stop going this way and to start going that way. The entire point of baseball is to cause an impulse. That's the whole point of the game, at least from the batter's perspective. So, this baseball is being thrown at the batter. It has this mass and this velocity. But unfortunately for the person who pitched this baseball, the batter in question is Babe Ruth. So, additional numbers that we have that the problem tells us about how Babe Ruth managed to hit this particular baseball. So, the ball approached Babe and the bat at 44.7 meters per second in this direction. After Babe hit the ball, it turned around and is now moving at 69.4 meters per second in the opposite direction. The ball has the same mass, but it now has a different velocity. It has changed direction and is moving very fast towards the outfield. The problem also tells us that the ball was in contact with the bat for a total of 0.71 milliseconds. That is milliseconds. That's not many seconds. All right, milliseconds are very, very small. Keep that in mind. So, let's go through the three things that this slide asks us about this very particular day in Babe Ruth's baseball career. First thing we are asked, what is the initial and final momentum of the ball? So, momentum is equal to mass times velocity. So we're just going to use this formula twice to find the momentum of the ball before Babe hit it and after Babe hit it. In both scenarios, the ball has the same mass. So for both of these, both initial and final, so I've added subscript zeros for initial and subscript F for final. In both of these scenarios, mass is going to remain identical because it's the same ball, nothing happened to the ball's mass. We're told the mass of this baseball is 145 grams. We need to change that to kilograms. We have our conversion to kilograms is 1 kilogram is 1,000 grams. So We want to move the decimal place over 3 times. The mass of this ball in kilograms is 0.145. 0.145. And then we're going to multiply by the velocity of the ball before and after. Before impact, the ball was moving at 44.7. After impact, the ball was moving at 69.4 in the opposite direction. The direction of the ball is very important here, because velocity is a vector. The direction matters. If you think about it, if we just looked at these numbers and tried to find the change in velocity, the difference between these two numbers would be about 15 meters per second. If we just looked at these two numbers alone without considering the direction. But once we take the direction into account, the ball was initially moving in this direction, meaning that Babe had to slow it down to 0 and then make it go up to this speed in the opposite direction. So the actual change in velocity of the ball isn't 15 meters per second. It's actually about 115 meters per second. The change in velocity of this ball is huge. And this is why so many good batters just completely destroy baseball bats, because they have to put out a lot of force to be able to change the ball like this. So, we need to take into account the direction here. And the way we do that is by making one of these two velocities negative, because they are pointing in opposite directions. One of them needs to be negative. I'm going to say, the way that I have drawn it, rightward is usually positive, so I'm going to make the initial leftward velocity negative. So I'm adding my negative sign onto the initial velocities. Therefore, when we finish solving for the initial momentum of the ball, so 0.145 times negative 44.7, the ball had an initial momentum of negative 48 kilogram meters per second. The negative here implies direction, because momentum and impulse are actually both vectors. Momentum and impulse have to be in a direction. If an object has momentum, it is moving in a direction. It wants to keep moving in that direction. Momentum is a vector, meaning this negative sign refers to the direction it is pointing in. In this case, initially pointing in the negative direction. After impact, it's now pointing in the positive direction, which is why both of the numbers we have plugged in afterwards are positive. So we multiply 1.45 times 69.4, and the final momentum of the ball is 10.06 kilogram meters per second in the forward direction. So those are our two momentums, one for the initial, one for the final. Next question. What is the ball's impulse? Impulse is defined as the change in momentum. Again, this delta symbol here, the triangle, means change in. That's what it represents. So, the change in momentum, we want to subtract the final momentum minus the initial momentum. Delta, change in, always means final minus initial. It is now final. We're subtracting out what it once was. So, our final momentum is positive 10.06. We're going to subtract our initial momentum, which is negative 6.48. Those negatives are actually going to cancel out, and as a result, when we add them together, and I'm going to show you how I put this in my calculator, you have 10.06 minus, open parentheses, negative 6.48. That's going to tell us the impulse of the baseball is 16.54 kilogram meters per second. which is a lot. That is a lot. We'll show that that's a lot when we look at part C. The last question on this slide asks, what force did Babe have to apply to the ball in order to make this happen? So, the question wants force. Now, we know impulse, we want force. We also know time. We know the time that the ball was touching the bat. We are told, the ball was in contact with the bat for this amount of time. So we know impulse and time and want force. So the formula we can utilize is impulse equals force times time. So impulse equals force times time. Our impulse is 16.45. We want to solve for force, so we need to plug in time. Now, we know the time that the ball was in contact with the bat, but that is given to us in milliseconds. Milliseconds. So we are going to need to convert this to proper seconds, and that's going to be 0.00071 seconds. Milliseconds are very small. They're 1,000 times smaller than base seconds. That means that the number of seconds here is going to be even smaller. So, we have 16.54 equals force times 0.00071. We need to divide both sides by 0.00071 to get our final force. I'm going to show you that in my calculator. And that's going to give us our final number. So, here we have, that is our impulse. We are dividing by time, and that's going to tell us the force that Babe applied to this baseball is a grand total of 23,295.8 newtons. That is tremendous. That is a lot of force. So, momentum and impulse. Do go back over the sections of this video as needed. Please report to our class calls for any questions that you have on any of these topics or any of our assignments. As this lecture goes up, I will also be posting the notes, the new homework, the new quiz, and the new lab. So, look over all. First, watch the video lecture and read through the notes, then begin working on those assignments. Come to our class times with any questions you have. I can go back over this material with you guys, work new examples, re-explain things, answer any questions you have. Thank you all. Have a fantastic day.